Okay. So this is the agenda for the day. You're more than welcome to go through all of this. This is actually Dr. Hussein's presentation. At the end of his presentation, we will have a conclusion as well as a post-webinar session where I will be explaining how to go through how to request for your certificate rather, as well as Dr. Hussein will be answering some questions you might have regarding to the topic that you might have. During the webinar, if you have any questions, please feel free to leave them in the chat box so that you are able to have them answered. You can as well as leave any EIT related questions there. I will be sure to answer them during the webinar. Okay, that's it from me for this portion of the webinar rather. I will leave you in the capable hands of Dr. Hussein. He will be presenting today's topic. Thank you so much for attending. Dr. Hussein, the floor is yours.
Thank you very much, Tasifu, and thank you very much. Good time to everyone, whether you are somewhere in the world, which is morning or evening. Good time to everyone. Today we are going to talk about energy storage systems, different types of energy storage systems that are being used in the power system, and we will touch base on how these energy storage systems can support the power system, especially under high integration of renewable systems. I am currently an electrical engineer and electrical lecturer at the EIT and a course coordinator for Bachelor of Electrical Engineering. Previously, I have been working at the University of Western Australia in conjunction with the company Magellan Powertronics. I'm working still with them. At some point of the presentation, I will talk about the project and the inverter that we have developed. And before I have been in few other universities, and I got my PhD in 2018 in Singapore. Let's start with the technical part of the topic. And in this presentation, I'm really going through some of the main topics without going very much details on any of them about energy storage systems. And there are, I think, 7 or 8 topics that we will be covering. The whole idea is to make you familiar with the basics of the system, main ideas of the system, and some of the research trends that are at the moment being used and being worked about in these systems. So let's start with what are the challenges that we have if we have a power system with high penetration of renewable energy. Of course, everyone around us is talking about the greenhouse gases, integration of renewable systems, and so on, and all the media are talking about these systems. But we, as an electrical engineer, not only see the advantages of renewable energy systems, but we need to also face the challenges that these new systems are making into the system, into our power system. Basically, the power systems that we have in all over the world, in different countries around the world, they are not really designed for renewable systems. They have been designed for a system that we have had big power plants, diesel power plants, fossil fuel power plants, and so on. And this system that has been designed for that purpose, we have started integrating renewable systems in it. And especially recently and nowadays, the integration of these renewable systems is increasing. Like you can see in the graph that the solar is increasing, especially here in Australia with a lot of sun, or in Africa with a lot of sun that we have, you guys have available, some of you. And on the other side, the decreasing price of solar photovoltaic systems. So the integration with the power system is increasing. Similarly, in some of the countries in Europe, we have wind systems that they have been integrated recently a lot in the power system. Besides the advantages that they have, we see the challenges. The first challenge that all of us are aware of is that the output power of these renewable systems are dependent on the environmental conditions. As an example, the output of the photovoltaic systems, a photovoltaic system that you can see in this figure, it just depends on the temperature, and it also mainly depends on the irradiance level that we have. As you can see, if it is a sunny day, of course the output power is kind of smooth, everything looks good. That's a kind of a good curve that we can get. But if they are facing a windy and cloudy day, the output power is going to be fluctuating. That's the first thing that we need to notice. Originally, the power systems or the power plants that we have had in the power system, we could control their output. Their output was not dependent on the environmental conditions. Like the output of a fossil fuel power plants is not dependent on the speed of the wind, for example, right? So we could control their output. But now we are having these renewable systems in which their output is not in our control. Their output is dependent on the environmental condition. Whether today is windy and the speed of the wind is high or low, I get different amount of power on that specific day, and so on. So that's the first change that we see. The system which is not yet ready, the system which is not yet designed for a fluctuation of the generation. What do we need to do? We need to smoothen down these fluctuations. How do we do? One of the solutions would be the energy storage that we are going to talk. So you can see for this first challenge, the main solution that we have is an energy storage, is any type of energy storage that I'm going to touch base a bit later. Once I say energy storage, I am not talking only about the battery energy storage. I'm talking about any type of energy storage system that can store electric energy in it. The next challenge that we have here is what we call as low inertia. Let me explain this a bit more. In conventional power plants, we have had these big generators, big synchronous generators that they were generating electricity for us. One of the main components of these big synchronous generators is the rotor, which is a big rotating mass with a big inertia. Now, first of all, you may say, okay, what's the usage of this inertia, or what does this big mass of inertia does? How does it help? What does it do to our system that I am concerned and I'm talking about? Okay, here I explain in a few sentences. The inertia of a rotor of a synchronous generator is one of the main parameters, if I cannot say the most important point, but I can say one of the most important parameters of a generator that helps to stabilize the power system. Why is it so? The inertia has an inherent response to frequency changes in the power system. If the frequency of the power system reduces, the rotor would give its energy to the load, so to keep the frequency similar to nominal, and vice versa. So you can see now we have had this big inertia of the rotors of the conventional power plants, and now what we do nowadays, we are just removing them because we are not interested in fossil fuels. I'm not also interested, but that's okay. But now we see, now we are removing this big inertia. We are removing the main important component in our power system that stabilizes the frequency, that makes the system stable. We are removing that, right? Because we want to go to a solar power plant, we want to go to a hydropower plant, and so on. In these systems, we do not have any more rotor, because like in a solar power system, power plant, we are using power electron converters. Power electron converters or inverters do not have any rotating mass. They do not have any inertia. That's why nowadays we have this challenge that the inertia of the power system is decreasing, so-called low inertia power systems. And okay, again, you may think, okay, what's the problem with the low inertia? I don't care about the inertia. What's the importance of inertia that you are talking about? The answer is this. Low inertia power system have higher stability issues. They are prone to be unstable. Because as I mentioned, the inertia is one of the main components that makes the system stable. I mean, to understand this, if you're looking for a keyword, you can look for what is called a swing equation in a synchronous generator. And by looking at, you would see the importance of inertia in the power system. Now, what's the solution? We are removing the conventional power plants because we are not interested in fossil fuels because of several reasons. We are using inverters for renewable systems because they are how they work. We have reduced inertia. What's the solution in this power system? Again, I need to go back and repeat this sentence. Our power system has not been originally designed with this low inertia feature. How do we improve that? We need to use energy storage systems to emulate the inertia. I will talk about it. And again, coming back to this graph, you can see in a low inertia power system, any change in the load will have higher impact on the frequency. And higher impact or higher changes of the frequency means higher chance of the power system being unstable. So again, energy storage systems are a solution here. They are going to help us with this low inertia issue. We have a lot of other challenges that we have. For example, another one that I can talk about here is lack of visibility of our generation. Now you can see, again, you go back to conventional power systems, we have had these centralized power systems. Their output power was visible, was known to the power system operators. They could plan based on the output power and so on. But what is happening nowadays? We have, for example, PV inverters that are installed in our houses. These PV inverters may not be connected to the network. They may not report their power at all. So now we have our generation, or in other words, I can say, we do not have visibility of our generation because now the generation is sitting in your house, in my house, and the power system operator does not know whether, for example, the inverter in my house is operational, how much is its output power, and so on. So that's another problem that we have. How do we solve that? Again, the main solution would be energy storage. I may not have visibility on the output power of the photovoltaic systems, but me as a power system operator, if install a big energy storage system, I can monitor its output. I can monitor its operation. Right? So again, the solution for the third challenge would be what we call as energy storage systems. Similarly, we can talk about lack of central control and so on, but I'm not going to continue. I will not here continue telling about these challenges. So the simple message that you have seen, you should have received now so far from this presentation is that integration of or high penetration of renewable systems in a power system results in a lot of challenges for power system operators. The main solution to all of these challenges is installation and integration of energy storage systems. How do we now, in this part of the presentation, let's look at different technologies that we have as energy storage. As I mentioned at the beginning, once I talk about energy storage, I do not really mean only battery. We have a lot or several types of energy storage technologies that are already being installed, already being used. One of the main ones is mechanical ones. I talk about two types of mechanical parts, which one of them being flywheels, the other one being pumped hydro. I will touch base on these two technologies. But beside this, we have other technologies to store the energy as mechanical. Then, as a second type, we have electrical ones that under which we can think of like supercapacitors or superconducting inductors. Another way to store the energy for us would be thermal. Another way would be just chemical, like storing as a hydrogen, or like in hydrogen-based energy storage systems that they use electrolyzer to generate hydrogen and they use fuel cell to generate electricity. And the last part would be electrochemical reactions or electrochemical technologies to store the energy. And here, under the electrochemical one, we have the batteries. We will talk about few types of batteries in this presentation, but for your information, we have more than 10 or 20s of different types of battery systems or battery technologies already available in the market. And you can see from this graph, in opposite to what most of us may think, that the battery systems are the main asset to store the electricity nowadays, you can see the answer is opposite or different. Mechanical based technologies that I will touch base on few of them now are the main sources or are the main solutions to store the electrical energy. Now, I'm going to talk about 3 or 4 different types of energy storage systems, just for you to get familiar with some of them. But you can see the previous table or previous slide, I had dozens of solutions. And by that, if you are interested, you can go and look at different technologies, understand their algorithm and so on. So, one of the examples that we have beside energy storage technology or storage technologies, beside electrochemical would be what we have as flywheel. You can see a flywheel, a simple flywheel in the slide. A flywheel, it emulates the operation of a generator. It will have a small generator or big generator with it, but the main part of the flywheel is a big mass or big with high inertia that keeps rotating. And if you think now, this is similar to a rotor of the synchronous generator. So you can see the first solution that we have, and we are talking as a way of storing the energy or as a way of energy storage, would be flywheel, which is an emulation of the synchronous generator itself. In a synchronous generator, however, we are generating electricity, and the source of electricity or the source of energy is from other types of energy like solar, wind, hydro, and so on. But in a flywheel, we get our required energy to rotate from the grid itself. And by that, the first thing that you may think of, if my flywheel system should have very high efficiency. Otherwise, instead of storing the energy, it is just converting the energy to loss. And that's why it becomes important to design a flywheel system in such a way that it has minimum power losses in it. So, and that's one of the reasons that flywheels are normally installed vertically. That's because of the same issue. So on the bottom, we have the mechanical bearings with magnetic bearings that they try to reduce the friction on on this part of the flywheel. On the top side, again, we have the motor or generator here in this case, which is most of the time a synchronous motor or synchronous generator. That synchronous motor or generator is connected to the grid through an inverter, or AC to DC, or DC to AC converter as well. So now you can see the first thing that we are talking as a type of a storage is a flywheel, and it stores the energy now as a mechanical energy because it stores the energy by rotating the flywheel rotor, and the higher speed that the rotor has means it has higher energy in it. That's the first type of energy storage that we got familiar with. There is another simple type of energy storage that we call as pumped hydro energy storage. In this technology, we simply store the energy as a potential energy in the water. So what we do during the day that we have, or during the time that we have excess energy from renewable systems, we just store this energy by pumping the water from lower reservoirs to the higher reservoir. And now the water that is stored in higher reservoirs has higher potential energy. And this potential energy can be converted back to electricity by flowing the water from the top reservoir to the bottom one and flowing it through a generator. So you can see this is another way of storing energy. During the day, I pump the water from the low reservoir to the top one to store the energy, because during the day I have excess power from the photovoltaic systems or renewable systems. But during the evening time that I do not have enough power from my generation, or I have lack of energy for my loads, I would just let the water to flow down from the upper reservoir to the bottom one, and that converts its energy or potential energy to electricity. Again, you could see another type of energy storage. The third one, which is again a mechanical technology to store the energy, is what is called as compressed air. In this case, as the name mentions, we compress the air from the normal pressure to a compressed pressure to a compressor, which needs the energy from the grid. So during the day, or during the time that we have excess power from the photovoltaic systems or renewable systems, we store that energy as compressed air by increasing the pressure of the air in our reservoir or tank and so on. Sometimes, or most of the time, we use or we store the energy in the ground itself. And then the only time that I need energy for the grid, that energy can be converted from the compressed air tank and through the expander and generate electricity for us. You could see again, this is another type of energy storage system. Again, of course, there are multiple other energy storage technologies that we don't need to go and talk about them one by one, but here you can see a comparison of these energy storage technologies. You can see on the x-axis we have the capacity, and you can see we have higher capacities for, let's say, the highest capacity for pumped hydropower plants, and on the y-axis we have the discharge time, which means the duration or the amount of time that we can discharge the battery or discharge the energy storage system from fully charged to no charge. Interestingly, pumped hydro stays in the top right of the figure, which means pumped hydropower plants are going to have highest energy level or highest capacity level, and their energy can be discharged for the longest time. After that, we have the compressed air, and on the very left side of the figure, we see the flywheels. You can see flywheels, they have low nominal powers. Their nominal power is in the range of 10 kilowatt, but their discharge time is relatively high. That means I have a relatively small flywheel, but I can store energy in it or just discharge it for a long time. And you can see in the middle we have the batteries, which have a relatively wide area. There are batteries that they generate high capacity but with low or relatively low discharge time, and there are batteries that do vice versa. So we will talk about the batteries soon. So by this topic that I have just passed through, is the main aim was to get you familiar and make you understand that there are different types of energy storage technologies. One of the big types of energy storage systems that has been used in recent years a lot, and it will be continuing used, is battery storage technologies. So let's have a quick look on different types of battery systems. First of all, you can see the installation of the battery systems have been or has been increased in the last few years. There is a drastic change or drastic increase in the last few years. There are different reasons for that. One of the main reasons is the price of the battery system that is reducing. And the other reason is the battery production. You see, nowadays we need batteries for a lot of different applications. We need batteries for energy storage systems, we need batteries for EVs, we need batteries for standalone power systems, we need batteries for microgrid, and so on. So there should be companies to produce and manufacture batteries. But I can tell you at the moment that we are talking, there are not enough battery manufacturers in the world that can supply enough battery to the whole world. That's one of the reasons. But every year, with higher technologies, reduced prices, and so on, the battery manufacturers are getting stronger, and they can supply more batteries. And that's one of the reasons for these steep changes. And this keeps changing and increasing every year, especially nowadays with uh, with uh, uh, sudden change or sudden increase on electric vehicles. Thank you very much, Charles. Yes, another sustainability, as I mentioned, the problem so far at the moment still that we are talking is lack of uh, enough lack of sufficient battery production and sustainable battery production in the world. So now let's get familiar with some of these battery technologies. This is a very brief overview of just 3 types of battery technologies so that you kind of get familiar with a battery. The first battery type that we are talking about is lithium ion battery, which is the most famous, most used, most produced battery in the world. Most of, or I can say all the electric vehicles that you see around you, they use lithium ion batteries. All the high power energy storage system that you see around you, they use lithium ion batteries. Most of, or more than maybe 70–80% of hybrid photovoltaic inverters that we install in our houses, they use lithium ion batteries. So you can see nowadays lithium ion batteries are the most used, the most manufactured, and the most interesting one. The main reason here is they have high power density. They can generate more power, or they can generate higher amounts of energy in a smaller volume of material. How does a lithium ion battery work? Any battery, this is not related just to lithium ion battery, but any battery, being lead acid, being sodium sulfur, being any type of the battery, has 3 main components. One is what we call as cathode. We have anode, and then we have cathode and anode. Maybe I put them together, and we have electrolyte, in which is the medium to let the flow of ions in the battery system, and in the middle we have what is called as separator. So here the important thing for us is that the battery works based on electrochemical reaction, which means first of all it has a chemical reaction in it, and within this chemical reaction there will be electrons that are free now, and these free electrons make the flow of water, power or current in a battery system. The main duty of the separator here is to let the ions pass through, because a simple explanation would be ions, either ions of lithium and so on, would pass from the cathode to the anode, and on the other side we have electrons that pass through our electrical circuit, which is connected either to the power system, connected to a lamp, and so on. And that's how the main picture works. Now, the separator, which is between the anode and cathode, it should be designed in such a way that it can just let the ions to pass. Again, I repeat, it should just let the ions to pass, not electrons. Even though electrons are normally smaller than ions. But the separate duty is to just let the ions to pass, because we have another thing, another important factor in this battery. I have two plates, being one of them cathode, one being anode, and there is a voltage difference between these two plates. So they can short circuit because there is normally a liquid water or liquid electrolyte between them. Now, another beauty of the separator is to ensure the electrical isolation between the two sides of the battery. Right? So now, in this, specifically in the lithium-ion batteries, we have two reactions. One reaction happens in the anode of the battery. In this case, positive lithium ions, they combine with the electrons that they come from the external circuit, and they generate LiXC. On the cathode side of the battery, we have lithium oxide, which is LiXO2, and is being converted to ions of the ions of the lithium and electrons. Now you can see the ions of the ions of the lithium are the material or the components that are going to flow through the electrolyte as well as the separator and move from one electrode of the battery to the other one. There is an overall, of course, reaction that we can write for that one also. So lithium-ion batteries, regardless of their basic operation and the chemical equation that I showed here, their main advantage here, as I mentioned, is their size. Here we define that as power density, which is defined as the amount of power that can be generated from the battery divided by the volume of the battery. So this is about lithium-ion batteries. A lead-acid battery also works in a similar manner, but we have different electrochemical reactions. Another type of the battery, we call it a sodium-sulfur battery. You can see the electrochemical reactions. In one side, we have the Na, which is sodium, that is being converted to Na plus, which is the ions of the sodium, and they are going to travel from the positive electrode to the negative. On the other side, we have sulfur that is being that is having interaction with the two electrons that they come from the electrical circuit and generate S2X minus. And as an overall, we are going to convert Na plus S to Na2S, which we call it as sodium sulfur. The main feature about sodium sulfur battery is its high temperature. Normally it should operate above 300 degrees. So, which makes it complicated. That's why we are not using, for example, sodium sulfur battery systems in electric vehicles, because it is going to be expensive. It's going to be safety issues with increasing the temperature of an electric vehicle battery to 200 degrees on one side. On the other side, sodium sulfur batteries are much safer compared to the lithium ion battery. And again, I need to repeat this sentence here, that the main challenges which we have with lithium ion batteries is their safety. And that's why we need to understand, and that's why we need to be very much careful about the sorry, and that's why we need to be very careful with the operation and safe operation of what is called as lithium ion batteries. The third type of the battery that I would like to discuss here is called as a vanadium redox flow battery. This is a very new technology. It has not, I mean, it is most of the companies that they work on this still, they are in the prototype stage. You may not find it commercially installed, right? Maybe mainly because of the prices and so on. But here there is a big difference between this battery type and the previous types. And the main difference here is the scalability. And what do I mean with the scalability is that we always have, in this battery system, we always have a tank of vanadium, which could be V2 plus, V3 plus, and so on. And the gas, the vanadium gas is being pumped into our main battery cell. And there is electrochemical reactions that are happening. And afterwards, the new material would be again restored and taken back to another tank. So the main feature that we get here is the ease of scalability, because to make the energy or to double the energy rating of this system, I simply need to do one thing. And that simple thing is just increasing the size of the tank. I don't need to increase the number of cells that I'm using. I don't need to make my battery bigger. The only thing that I need to do here is just increase the size of the tank. So now you can see this is the main feature, and this is what makes this battery type more interesting nowadays. And it may replace the lithium-ion batteries for different reasons as well. So we got familiar only with 3 types of batteries and battery technologies. Now we need to understand their performance. How do they compare? What battery type should I use? And so on. There are a lot of different performance indicators for selection and comparing the batteries. I'm going to just talk about 2 different ones. The first one is what we call as voltage performance. Comparing a lead acid battery and lithium ion battery, the main difference that we can see from this curve is that a lead acid battery and lithium ion battery, the main difference that we can see from this curve is that a lithium ion battery has a relatively constant voltage, constant terminal voltage over a wide range of state of charge or depth of discharge, in other words. This makes this battery system interesting because this battery system has constant voltage and it can supply the world with constant voltage. On the other side, a lead acid battery that you may only have seen it in your car, as if you are driving a combustion engine based car. That is the only place that you may have seen or you may see the lead acid battery. And the main disadvantage of lead acid battery, I mean, in this case, comparing it with lithium ion, is that its voltage is going to change over the range of the state of charge, which means if I charge the battery higher, its voltage is going to increase, and vice versa. This simply means I cannot simply install a load directly to this battery because the voltage of my load is going to be changing. And okay, this is just a comparison between the lithium ion and lead acid. But then you can look the comparison with other types of batteries as well. In the answer to your question, Elizabeth, we have on the vanadium or fellow type batteries, I am aware that in Australia there are companies producing it. I am also aware that there are certain companies building these vanadium fellow batteries for residential usage because of its higher safety. On the sodium sulfur, I am not 100% sure of its commercial availability. And another type of storage that I can talk beside the batteries are capacitors and fuel cells. Capacitors or supercapacitors can store the energy for a very short amount of time. And fuel cells on the other side, they are based on hydrogen. Once we say about the fuel cell, at the same time, we normally also have an electrolyzer. The process would be to use electricity to generate hydrogen, and then we use the fuel cell to generate electricity back. And so now we can simply compare different types of battery systems. And that is one of the factors that we need to consider in selecting the battery. If I am selecting the battery for electric vehicle, I may have different criteria than selecting a battery for energy storage. In electric vehicle, I am looking for something compact. I'm looking for something that can generate electricity for maybe few hours so that I can drive maybe 100 kilometers a day and so on. But the same thing, once it comes to the energy storage, I have a different factor, which is the high amount of energy that I can store. In an energy storage system that is installed in the power system, I'm not concerned about the size, about the weight, right? So now we can see the comparison in this side, which means we are comparing the batteries based on their specific amount of power, which is classified or calculated based on watt per kilogram, and on the specific energy, which is the energy or watt hour per kg or kilogram. You can see lead acid batteries are having the lowest performance here. They have lowest power density and lowest energy density. On the other side, we have different types of lithium-ion batteries like this one in the blue, which is our commercial lithium-ion batteries. They are having a wider range of energy and specific power. Capacitors on the other side, they have high specific power, but not energy, and so on. So it becomes important as one of the factors. What is my application, and what factors should I consider in the design? Another thing that we need to consider in your response, Crane, if I'm not pronouncing your name wrongly, is the type of the load that I have. Sometimes I have a load that requires high amount of power but for a short time. That means I need to select a battery that can discharge fast, because one of the important factors in these batteries is their discharge rate. Sometimes I can discharge the battery with their nominal power or nominal energy rating. Some of the batteries I can let's say half of that, and so on. So this is another important factor that I should consider. And yeah, I have also summarized this. The comparison is stable. The main, I mean, I'm repeating few of them here. The lead acid batteries, the main usage is advantage is they are low cost and their technology is mature. That's why they are still being used. And but on the other side, on the lithium ion batteries, we have high energy density, but they are very costly. On the vanadium redox or flow batteries, we have high energy storage capacity and so on. Now, due to the time, I'm going to go a bit faster from now on, just touch base some of the main points. Now that we have the battery, we have discussed about it, we need to discuss on how do we connect this battery to our system, to our power system, because we need a power converter to connect it. As you know, the output voltage of the battery is a DC. On the other side, our power system is an AC. That means we need a power conversion stage. There are different types of power converters that have been used and are being used in the power system as power converters for battery systems. Some of them are based on transformer that I'm going to talk a bit later, like two-level and inverters and so on. Some of them are solid state based, which I can say for them a two-stage with LVDC link, three-stage, and so on. You can look at the article to understand these technologies better. And some other are transformerless that I will touch base on two of their technologies. So now let's look at a simple or a conventional way of connecting a battery system to the grid. You can see in this configuration, I have the battery which is rated at 1000 volt. I have a two-level inverter here. Of course, I would need some contactors and pre-chargers on the battery side. And then in the output of the inverters, we have normally LC filters or L filter and so on. In this case, the power converter is using a transformer for connecting to the grid. And that gives us an overview, a simple power converter for connecting the battery to the power system. To get you a bit familiar now with the real things, I have showed you a 100 kilowatt energy storage system in this figure. So the top on the figure, the enclosure on the right is a 100 kilowatt inverter, which as part of the project that we had with Magellan Power Electronics, we designed, tested it. And the left side, this big enclosure that you can see, they are lithium ion batteries. If you count, you would see 24 battery modules. These are lithium ion batteries that are being installed. The system itself is a 100 kilowatt hour system and its weight is only around 1000 kilogram. If you want to reach the same energy with lead acid batteries, you may need 5 tons of battery. And that, by that, I hope you understand what's the difference between what do I mean with power density. If I use lithium ion batteries to get 100 kilowatt energy or 100 kilowatt hour energy, I just need 1000 kilogram of battery. But if I use lead acid batteries, I may need 5 times or 10 times more. That's why the power density and energy density of lithium ion battery is much more than a lead acid batteries. All the power converters on the other side, they need a brain to control them. And that's where we, as power electronic engineers, would work on. We normally use, or in other words, I say, we always need to use microprocessors or microcontroller units to control these systems. And this is an example of one of these topologies that has been used and installed in this battery inverter system. What you can see here, again, this big battery system that you can see, I highlighted here, and you can see some of the battery modules here. This is a, again, lithium ion battery. This is 200 kilowatt hour battery system. If you compare these two, you can see this one compared to the second one is much smaller on a size, and that's why this we have higher amount of energy available in the second one. So a lot of times once we have high power battery energy storage systems, we need to connect these battery energy systems to we need to connect these systems to high voltage power system. So to connect to high voltage power system, we either need a transformer like the previous configuration that I mentioned, or we need to go transformerless, because using a transformer is costly. It is a bulk transformer and it reduces the efficiency of the system. However, if I want to remove the transformer, I need to come up with another solution to be able to connect to high voltage systems. The main issue or the main challenge is the semiconductor or the semiconductor switches that I have available. The semiconductors that we have nowadays available, or IGBTs in other words, they are only 2 kilovolt. If I want to connect my system to 20 kilovolt, I cannot use directly them. So there are few solutions here. One solution is, okay, let's just put more and more semiconductor switches in series to reach to the voltage or the required voltage that we need. Another solution is to make this a bit more smart and use what we call as a new technology of multi-level converters and multi-level inverters. In these systems, we, instead of using multiple switches in series, we connect converters in series. Now, in this case, once we have high voltages in our DC link or our battery system, we require multiples of battery modules connected in series. The batteries, being either lithium ion battery and so on, the batteries are not going to be exactly the same. They are going to have different aging. They are going to have different operational conditions. And that's why when we are charging them or we are discharging them, their voltage, their amount of energy is not going to be the same. And this is where we require what is called as battery management system or BMS, in answer to your question, Kamran. So a battery management system that you can see one example on this figure It simply manages the battery statuses or the battery modules in this whole power system. Because you can see, if I go back to this figure, I have 36 battery modules connected in series. So I need to ensure that these battery modules, they get similar amount of charge and similar amount of voltage. And that's the duty of the BMS or battery management system. In the figure here, I know it's not very visible, but the one on the top, this module on the top is doing the battery management system. It simply needs to communicate with all the modules and make sure they are balanced. Battery management system is not only between the modules, it should also happen between the cells. The main reason, again, especially for the lithium ion batteries, is that these batteries are prone to safety issues. They are very sensitive to be overcharged or over discharged. That's why we always need to have a balance between the cells and modules. And this is another battery management system that you can see is connected between the cells. It regulates the voltage and the current through them. On the other side, energy management system, it looks on an overall system, and when an inverter is connected to the power system, in a power system, I may have diesel generator, I may have some other types of loads, other types of generation, PV, and so on. Energy management system is going to have communication and regulation between these different types of energies. And as the last part of this presentation, I quickly touch base on power system supports that we get. Now, at the beginning of this presentation, I mentioned about the challenges that we have in power systems with high penetration of renewables. Now, at this point of the presentation, I would like to discuss how can battery systems help to improve and support the power system. One of the ways they can do is through what is called as frequency support. A frequency support is when a battery system can reduce its output power or increase its output power if the frequency of the power system changes. Another word, you can see an example here. If the frequency of the power system reduces due to an event, the output power of the energy storage system or battery system can increase, right? And this increase is similar to the behavior of a rotor or a synchronous generator. That's what the synchronous generator does. A synchronous generator increases its output power if the frequency of the system decreases. And a battery system can do the same, right? So you can see this is one of the supports that we can get from the battery storage systems. Another way battery systems that can support the grid is through voltage, in which they can increase or decrease some amount of reactive power injection to the grid. And that's another way of supporting the power system. In 2 minutes, I'm going to just touch base 2 more important parts that I wanted to discuss, but you will have access, I guess, to the slides later on. So one of the important things that now we have as a safety standard in battery system is what is called as arc flash. You can think now, to make it a bit more sensible for you, you can think A battery is a source that has stored electric energy in it. This source, if there is a short circuit in this source, what is going to happen? You have chemical reactions, you have electrical reactions, you have heat, and that means explosion. And that's something that you have seen for electric vehicles. There are a lot of explosions. You have seen the fires or explosion in energy storage systems and so on. These are because of this. And now, this is one of the safety issues that we need to address. And to address them, one of the things that we need to consider, we need to quantify. We need to be able to quantify how safe is a system, or how bad is the safety of the system. And one of this quantification algorithms or the indexes is what is called as arc flash. Arc flash is that if I short circuit a battery system, how much energy, you see again I'm using how much energy can it produce, right? And there is a certain equation for that, which depends on the voltage of the battery system, depends on the time that we have the arc, and so on. And another important thing is that depends how far from the battery storage system this short circuit happens. And to do that, to deal with this, there are standards, there are safety standards that they impose different levels of protection, or PPE. Once we quantify the arc flash, based on the arc flash that is quantified, we can determine the safety level that we need to wear or use once using the battery. So as emerging technologies, one thing is we can operate the photovoltaic systems similar to battery systems. So that nowadays that we have cheaper photovoltaic panels, cheaper photovoltaic systems, we can use these systems and reduce the cost of our system. Another important thing that I would like to just mention in 1 minute is the electric vehicles. You may see, especially here in Australia, you could see in the last 1 year or 2 years, the number of electric vehicles on the road has been drastically increased, right? All these vehicles are going to have a big pack of battery systems, which are currently mainly lithium-ion batteries. Now, these batteries, one of the issues they have is their aging. These batteries are going to be aged normally after 7 years, 8 years, 10 years, which means they need to be replaced. Here, you need to know, what do we define as aging? Depending on the application, for example, for an electric vehicle, once we say the capacity of the battery is decreased to its 80% of nominal capacity, we say it is end of it for an electric vehicle. What does it mean? I mean, in other words, means if you get a new electric vehicle and the first day that you are using, you can, let's say, drive 400 kilometers. If after a few years, with the full charge of the battery, you can only drive up to 320 kilometers, that's the end of it. Because normally you get tired of it, right? We say, I want to go 400 kilometers. But that battery that is not good for your EV anymore, you don't like it, can still be used. And that is what we call a second life for battery. So the battery that you have in your EV or electric vehicle, once it is end of its use in a car, it can still be used as energy storage, right? Because again, you can see different factors that we need to consider. In electric vehicle, I'm looking at the weight or the density, but an energy storage, I can put it in a very vast area, right? I don't mind. Another thing though, nowadays that we talk about this battery systems, everywhere is being used and so on, what do we do to recycle them? And this is what you have seen nowadays. What we call as now is the 4R. Especially this 4R thing you might have seen in different technologies, terminologies in different companies around the world. Simply means if I am using a battery in a car and it's end of its life for a car, I should reuse it or refabricate it or recycle it, because I can get the battery material here. And this is what, this is what, Charles, you are happy with now. Thanks. As a summary, we talked. Thanks. As a summary, we talked about the challenges that the power system face due to high penetration of renewable systems. We talked about different types of energy storage systems, with a bit more focus on the battery systems, about the power support, and few words or sentences about the new technologies and trends. That's all now from my side. Later, I will answer some of the questions that I could not answer during the presentation. Thank you very much.
Thank you so much, Doctor. A lovely presentation. I am pretty sure our prospects will agree with this. Ladies and gentlemen, we'll come to the end of Dr. Hussein's presentation. This is the time that you may ask him some questions. You're more than welcome to post them in the chat box so that he is able to answer those questions. Whilst you guys are doing that, I will be going through some post-webinar slides for some of the things that we offer, or courses rather, that we offer at EIT. This is our upcoming course schedule. These are the courses that will be starting in May. You are more than welcome to view our course schedule using the link. These are specifically in the range of renewable energies, and we do offer quite a lot of courses in that field at EIT. I will also share the course schedule link in the chat box whilst the doctor is answering your questions. These are our upcoming webinars. You are more than welcome to register for our next topics that we will be hosting. We have 2 in the month of April that will come after this one, and then we have several in the month of May that you are more than welcome to register for. I will share the link as well in the webinar box. Okay. Lastly, the certificates of attendance. Ladies and gentlemen, to receive your digital certificate of attendance, you will need to either scan the QR code that is up on the screen or follow the link that is up on the screen as well. What I will do is that I will put the link in the chat box as well, so you guys have easy access and are able to use it in order to fill in the Microsoft form. As mentioned in the beginning of the webinar, you will need to fill in the form in order to receive your certificate. Now, the form will be live from today up until the 22nd of April, 5 a.m. UTC time. Unfortunately, no further requests will be taken for the certificates after the form has closed. So please, if you could kindly scan the QR code or follow the link that I will input in the chat box whilst the doctor is answering some of your questions, and then you guys will be able to receive your certificates of attendance. Now, how the certificates will be distributed: on the day after the webinar Microsoft form, that is the form that you use to fill in your details in order to get your certificate. The following day after that, you will receive your certificates. just 2 business days after that, you will receive those certificates on email. Be sure to put in your names exactly as how you'd like them to appear in the certificate of attendance, as well as other details that are needed on the Microsoft form. Okay, this is the time for you guys to ask your question to Dr. Hussein. He actually went overboard his time, so about 10 minutes more, you guys are welcome to ask him while I will return to the QR code as well as the link so that you guys are able to scan and fill in the Microsoft form in order to request for your certificates of attendance. So I'm just going to leave your questions. I'm just going to leave you guys to ask your questions. Dr. Hussein, I do think you have about 2 more that have just appeared in the chat box. And then after 10 minutes, we will close for the webinar so that the doctor will have some time. Thank you so much, guys. I will leave the doctor to answer your questions.
Thank you very much. Yeah, I have read most of the questions. Some of the questions I don't really know the answer, but I will go through one by one. First of all, thanks, Mohammed. You have asked about, I would like to know your opinion on using carbon dioxide capture from either the carbon capture or direct air capture process in CO2 battery systems to store energy and cut down CO2 emissions compared to lithium-ion batteries regarding both systems, efficiency and cost. Honestly, I don't know the answer to this question because I'm not very much familiar with CO2 battery systems. Sorry for my lack of knowledge on this side. Kindly advise which storage technology is best for data centers. Ronald, this, as I mentioned, this really depends on in a data center, I guess we are looking for the higher reliability of the system. And if the concern is still the what we call as the space, again, lithium-ion batteries might be possible, might be the best solution. But as a whole thing, again, it depends on the cost that you want to pay, as well as the location and the space that you have. There has asked, is it ethical or possible to combine solar and wind energy in a single energy storage system? Yes, why not? There are thousands of microgrids around the world who are combining these two systems together, and there is no problem with that. I'm not, of course, sure on the legislations based on the country and so on, but as a technical solution, as a technical answer to this question, the answer is yes. Can you explain, refresh the flow ions from the cathode of anode for lithium ion and lead acid batteries, as well as their respective power capacity in graphical depiction, for example, the discharge time periods? Can I change the slide, Sipo?
Lisa was muted. Yes, you may do so, Doctor. I've actually attached the link for the certificates of attendance in the chat box. Ladies and gentlemen, yep, you are free to utilize the link. Please fill it in so that you are able to get your certificates once the marketing team has wrapped up the webinar, slides, as well as the video, and mail them to you as well.
Thank you. So the answer to this question, the comparison of the discharge time periods between the lead acid and lithium ion is, lithium ion batteries, they can discharge with what we call as one discharge rate or 1C. For example, if you have a 100 kilowatt ampere lithium ion battery system, you can just discharge it in 1 hour fully, right? This is called 1C discharge. But this cannot happen for lead acid batteries. Lead acid batteries, normally they have longer charge and discharge rates. Normally you can think of 0.5C. For example, again, if you have a 100 kilowatt hour lead acid battery, you can discharge it in 2 hours. You cannot discharge it in 1 hour. And that also becomes important in selecting the battery type. Elia Haider asked what determines the quality of the photovoltaic systems. That's really depending on the chemicals and semiconductors that they use. Of course, their basic technology is the same, but the material that is being used makes a difference. That's why you have photovoltaic systems with higher efficiency. They are costlier. Depending, I mean, the main technology here, or the main technical answer here, is the amount of process that we do on the silicon to make it pure, because you know silicon has different levels of purity. The higher purity you have in your semiclone and semiconductor, you have higher efficiency, but at the same time this means you have higher cost, and that is the reason that we have photovoltaic panels with different costs and efficiency. The other question, Atta asked, do you have any expert insights as to what further metals may be added to lithium ion to improve the battery storage? I know of some of the chemicals that can be used to increase the characteristics of the battery, but on top of my head, I don't remember the names that I can mention. This is fully chemical engineering. And sorry, I do not have very much detailed knowledge on that. Someone asked about the difference between the power density and energy density. I hope you understood based on my explanation of the two figures. Olabut asked, what is the best battery system for a mini grid solar power solution? Again, I don't really know what do you mean with the best here, but you know, the selection of the battery depends on various factors. First of all, the size of the battery depends on the load, the duration that you need to supply the load, how much power you need to supply to the load, and so on. The technology of the selection of the technology of the battery depends on the cost that you want to pay and space that you want to have available and the safety that you have available. So this, I mean, really depends on different parameters, and there is no a single answer to this. Someone, yeah, Ronald or Roland asked, can the same battery be used for both frequency and voltage support? Yes. It's the inverter job. It can generate different voltage and frequencies, and that's how it can provide the two functionalities at the same time.
I think the last question you have, Doctor, is from Aubrey. It's right at the bottom of the questions, and it says, I have seen battery storage systems being integrated with the grid with highly industrialized economies with the sudden demand of inductive loads not led to a grid collapse. I'm not sure if that is a question or a statement. However, that seems to be the last of the questions you might have. The other questions are for me regarding the links to the certificate.
Okay, thank you. So I guess, yeah, I know that, again, to continue with the comment that Aubrey mentioned, yes, the battery systems, especially the lithium ion bonds, that they can provide higher C discharge rates, which means they can provide sudden output power change, are being used in the battery system that we have also designed. We have considered that, and we are able to supply, let's say, the starting of the motors with 6 times nominal current and so on. So this, from the battery side, that's something technically possible. And thanks for the comment. Thank you everyone for attending the session. Yeah, I also write my email here in case you guys have any question. You can email me as well. Thanks everyone. Thanks, Sipo.
Thank you so much, Dr. Hussein. Ladies and gentlemen, that concludes our post-webinar session. I'm just going to quickly go to our last slide so that I am able to provide you with the QR code as well. I'm just going to wait for about 10 more minutes so that you guys have access to the QR code to request for your certificates. Alternatively, I've also included 2 links the chat box that are viable for you to actually be able to request for your certificates of attendance. Okay, that should be it. Up on your screen is our email. If you go to the EIT website, you'll be more than welcome to contact us. There are several channels or platforms where you'll be able to contact either a course advisor or an EIT staff member who will be able to actually send you any course information that you might need or direct you to the relevant people who will be able to help. Emmanuel, the links to the certificate of attendance are in the chat box. Please go to the chat box. You'll be able to receive the links. They are there. I unfortunately cannot email it to you. However, I'll just include it once more. I'll include all the links I've shared so that you're able to actually have that certificate of attendance. Just kindly hold on for me. Henry, the slides are going to be emailed to you. They will be emailed to you within 2 business days. And then the certificates of attendance, you'll receive them after after the time has elapsed for the certificate request form. As you can see up on the screen, the certificate request form will close on the 22nd of April, Monday morning at 5 a.m. UTC. You will to get your certificates after 2 business days from Monday. So around Tuesday, Wednesday, and Thursday, around those days, you'll be receiving your certificates, provided that you actually did fill in the certificate request form. You will be able to receive your certificate from the EIT marketing team. Okay, if we don't have any more questions after that, ladies and gentlemen, I will be leaving you. I will keep the slide up on the screen. I'll just be turning off my camera. However, you'll have the slide up on your screen in order to request for your certificates for the next 8 minutes or so, and then I will stop the recording and close the webinar. Thank you so much, Dr. Hussein. Hoping to see you next time on another webinar. Thank you and have a lovely day.
Thank you very much. Thanks everyone for attending and have a good time. Bye. I leave the webinar. Thanks.
Problem, doctor. Thank you.
Thank you.